For the rest of the videos in this section, we're going to go ahead and start taking a look at some of the more simplistic numerical methods to be able to approximate solutions to differential equations. And one of the easiest one, in fact, the easiest one is just the original Euler's method. And I'll just go ahead and start with the diagram to make it really easy for everybody to see. If we have a curve, we can approximate the solution to that curve just by utilizing some linear segments. All right, so we could just go ahead and say, okay, well, A1 is the approximate solution to f at x1, A2, and we just keep getting the equation of the line and the endpoints of those to be able to figure out what the next guess is. All right, now the distance from A0 to A1 is h, the step size. All right, this is like we've seen in other videos. And so to derive that, what we could say is that given our step size, and I'm just going to say x1 and x0, we could solve it for h, and h plus x0 is equal to x1. We could just go ahead and use a linearization, all right? And we're going to say that y prime at x0, which is going to be the slope at the point x0, is going to be equal to our x minus x0, and then we just put the y0 on the other side. All right, so now this is just the slope to the next, and clearly the x0s are going to cancel out. The y prime is the slope at the prime x0, but that's just y prime, the original differential equation, right? Our function at fx comma y. And so we can get this really simplistic differential equation, or I'm sorry, numerical method, where we just take the function evaluated at the current x and y values, multiplied by the step, add the current y value, and that's going to give us the next y value. All right, so in other words, we get this derivation. All right, of course, if h becomes smaller, then we get less error in between. All right, but of course, it becomes more tedious if we were to do that by hand, but we're going to use MATLAB to do the lion's share of the work for this. All right, so the first time we do these algorithms, I'm going to go ahead and do this pretty painfully. So what we're going to do is we're just going to consider this pretty basic differential. 4x minus 2y, y at 0 is equal to 2. And we're going to use the dsolve function, and we're going to find y at 0, 0.1, 0.2, 0.3, 0.4, 0.5. And then we're going to use Euler's method to go ahead and approximate the error at each step, and then go ahead and approximate the same thing. All right. So in fact, by doing Euler's method with h equals 0.01, we will find 01, 02, 03, 04, 05 values for y. Right. So first of all, we're just going to use the dsolve function, and here's our differential equation. So let's get to it and program it. So we're going to have some sims variables. We're going to have our y at x and our dE solution. Right? And we're going to define EQU just like we've been doing as diff y comma x is going to be double equal to 4x times 3y, or minus 2y, excuse me. Right? And our condition is going to be that y at 0 is equal to 2. Right? So that's the initial condition. And then we're going to do a dsolve. All right, so I'm going to just say dE solution is going to be equal to our dsolve of EQU comma condition. All right, so now we have the analytic solution. All right, now I'm going to start the numeric solution. All right, so I'm going to define a new variable x1, and that's going to be our initial x value. Right, and I'm going to call current y. I'm going to call this current y value, or cur y is going to be equal to 2. All right. And again, what we're doing is we're just using this algorithm. All right. So I'm starting out with y is going to be equal to 2 and x is going to be equal to 0. We also need the step size h, which we already know to be 0.1. All right. Now I'm going to go ahead and do a for loop for this. So I'm going to say for I equals, now I know that I'm going to have 5 steps. All right, and here's how I know this. We have 0.01 is the initial value, and if we look at what the problem suggests that we end up at, we're going to end up at 0.01. 0.05, right? So we're going to need 5 iterations. We're going to need 1, 2, 3, 4, and 5. All right, so you kind of have to do a little bit of prediction before you go through and actually code this. All right, so if it was more than 0.5, then you would have, or less than 0.5, or a different h, then you'd have to kind of predict what your delta might be in this case and how many iterations you would need. All right. Now I'm going to go ahead and get the exact value at each of the points. All right, and I'm going to say exact is going to be equal to, we're going to substitute, and we're going to substitute into the DE solution. We're going to get the x as the old variable, and check this out. We're going to use x1, which is 0, but we already know what the value is at 0. We really want the value at 0.1, right? So then I'm just going to say x1 plus h, right? And that's going to give us the value, just to make sure we understand. This is the value at f, or at, when x is going to be 0 plus 0.1. All right. And then what we're going to do is we're just going to shove in that value back in. All right. Back into the DE solution. All right. So that's our exact. Now, to be able to get to our approximate, which I'm going to call the next y. All right. And I'm going to call this next y because if we look at our algorithm, we need yn plus 1. So that's going to be our next y. So I'm going to call this guy next y. I'm going to call this guy current y. Right? So that's going to be, next y is going to be equal to, now look at our algorithm. All right, algorithm says that we're going to take the current y, so I'm going to call that curry, plus, we're just going to evaluate the original differential at the current x and the current y. All right, so that's going to be, remember, our original differential is 4x, so that's actually going to be 4 times x1, because we defined a new variable, minus 2 times current y. And then the last thing that we have to do is we have to multiply that by the step size h. All right, so just going through using this algorithm, nice and easy. That's going to be our next y. We're going to get our percent error. So p error is going to be equal to the absolute value of the next y, because that's our estimate, minus the exact. And we're going to divide that by the exact and multiply by 100. Now what we're going to do is we're going to print everything out. Right? So we're going to do an fprintf, and we're going to print out a table. Now let's print out the current x. All right, and in this case, we're not looking at x is equal to 0. We're actually looking at when x is equal to 0.1, the next x. But we'll get there in a second. All right, so we're going to have a %f. Then we're going to have the estimated value of y. So I'm going to call that %f. And then we're going to have the exact value of y. And then we'll have the error. All right, so now when I'm doing this, I'm going to have x1 plus h. All right, that's our next x as we're doing this. All right, so x1 plus h is going to be our next x. All right, we need our next y. We need our current y, or we could just call it exact. All right, which is going to be the exact value. This is the next y, and then we're going to have our percent error. All right. Now, one last thing that we have to do is we have to update the values of current y and x. So x1 is going to be equal to the current x1 plus h. And what that does is that moves us on to the next x, right? So basically, if you were to look at the diagram that we had before, now what we're doing is we're just moving from A1 to A2, right? So we're just adding h to get to our next x each time, right? These are supposed to be individually segmented equally, right? We also have to redefine y. So we're going to say that current y is going to be equal to next y, all right? So that way we're done with the algorithm. All right, now the last thing we probably want to do is we probably want to get a heading for all of this stuff. So let's just fprintf a heading. and we're going to print out what the x value is, and then we're going to print out what the we had the estimated y, so I'm going to call this y estimate, and then we're going to have the exact y, so we'll just call that y exact, and then we're going to have our percent error. All right, so let's see what we get out of this, all right? Because we really haven't even run the algorithm to see how good of an approximation or how poor of an approximation we get. All right, so let's run it out. Hopefully no errors. All right, so we are in, oh, right here. That's not next, that's next y. All right, and we'll space this out just a little bit better. I'm going to run this a few times before I actually go through and. All right, so what do we get out of this? So we're taking a look at this, all right, and the first time it's not too bad, all right. By the time we're done getting up to 0.5 for the x, all right, we end up with an error of about 11%, all right. Keep in mind that Euler's method is just a really rough approximation. And if the original function is not necessarily linear, if it's kind of all over the place, like an exponential, or if the solution is an exponential, all right, then unfortunately, what's going to happen is we're going to get like some really big spaces in between, all right? In fact, let's take a look and see what the analytic solution is, just out of curiosity. All right, and it is indeed an exponential, all right? And we know that using a line to approximate a differential or an exponent, a line to approximate an exponential function might not necessarily give us the best results. All right, so although we do get to the results with a fairly large step size to be 11% error. All right, now in the next videos, we're going to take a look at algorithms that are going to refine this process, all right, to give us a little bit less percent error as we go along. All right, but hopefully this gives you a good idea of the algorithm that's necessary for this. And this right here is really the algorithm going on with this. All right, so this is probably the most important part to pay attention to. In fact, in our next videos, all we're really going to do is just change the algorithm each time.